Did you ever think about why a Mixtral 8x7b is a dense 47 billion parameter model and not a 56 billion parameter model? Because going by the pure arithmetic, it should be 56 billion, that is 8 into 7. And the reason is because mixture of experts or MOE models, only the FFN layers, that is feed-forward network layers, are treated as individual experts, and the rest of the model parameters are shared. So when Mixtral receives a request, the model's router component picks 2 of the model's 8 experts to handle the request. While all the 46.7 billion parameters are loaded into the memory, only 12.9 billion are used during inference. Again, not 14 billion as attention layers are shared. And why I'm saying 14 billion? Because if 2 experts are loaded and each expert is a 7 billion parameter, then it should have been 14 billion, but it is not. It is only 12.9 billion because the attention layers are shared. So similarly, during inferencing, assuming just 2 experts are being used per token, the inference speed, that is the flops, is like using a 12 billion model as opposed to a 14 billion model, because it computes 2 into 7b matrix multiplication, but with some layers shared. And when handling a single request at a time, Mixtral's performance is far better than larger models like Llama 270b because the request touches fewer weights. This improves both time to first token and also the TPS, that is tokens per second. So here is some fundamentals on the mixture of experts architecture. In MOE, we have, it actually consists of 2 main elements. The sparse MOE layers are used instead of dense feed-forward network layers, because in MOEs, we replace every FFN layer of the transformer model with an MOE layer, which is composed of a gate network and a certain number of experts. A gate network or a router that determines which tokens are sent to which experts. How to route a token to an expert is one of the big decisions when working with MOEs. The router is composed of learned parameters and is pre-trained at the same time as the rest of the network. So the gating function is typically another small neural network within the MOE architecture. It analyzes the input and calculates a probability distribution over the expert networks. The input is then sent to the expert with the highest probability, ensuring the most suited specialist tackles the task at hand. Also note that while there are inferencing services that achieved an FP8, that is a floating point 8 implementation that runs 3 experts for each token as opposed to default 2, but activating more experts is detrimental since the model was trained to work with the contributions of just 2 top ones. That's why activating 4 or 5 or more experts actually reduces quality. Now, this image is taken from the original paper of Mixtral 8x7b. Let's quickly go through it because this depicts the 8 experts that Mixtral model has. So, Mixtral 8x7b consists of 8 feed-forward blocks or experts in each layer. A router network dynamically selects 2 experts for each token at each layer, allowing access to 47 billion parameters while only actively using 13 billion, that is actually 12.9 billion during inference. And note that the 8 experts here are not trained or specialized in specific areas. That is, there is not an archive expert or another one GitHub experts, another one is on literature experts. There is no experts like that, because each of the experts, that is 1 to 8, is chosen at each time step, meaning each token can come from a different expert. What this table of experts is showing is how often the same expert was chosen for subsequent tokens. Some experts are chosen more often than other experts for each subsequent token. And these choices of experts has more to do with the syntax or the meaning of the text rather than the domain.